We were discussing about surface tension in the last lecture. So let's continue from that point onwards. So we had understood surface tension as a material property of any liquid with two major acts associated with the surface tension. One is the surface tensional force, or the sort of restorative elastic type of force that is experienced along the surface in a tangential direction for a fluid. And by that means, the surface tension as a physical property is defined as the tangential force per unit length. On a surface. Of course, a liquid surface. And the other property of surface tension that we had understood was the property associated with the elastic potential energy that is stored in a surface. We had also seen that surface tension is the elastic potential energy per unit surface area. Or in other words, the elastic energy of a surface is equal to the surface tension multiplied by the area. These are the couple of definitions that we had seen last time. Okay. And we had seen some problems based on this. So let's look at a typical problem based on the concept of elastic potential energy of a surface. So if we have this situation that a spherical drop of a liquid, the certain surface tension (200 millinewtons per meter). And radius, let's say 8 millimeters. So this has to be split into 8 identical spherical droplets. Find the work done by an external agent to split it. So this is a typical application type of question for the second concept that we have seen above over here, that surface tension is surface potential energy per unit surface area. So we'll use that concept over here. So previously, we had also understood that because the surface energy is surface tension multiplied by surface area, so any liquid body tries to minimize its surface area so as to minimize the surface energy and therefore have maximum stability. That's where we'll understand over here that a certain volume of liquid, when it is arranged into a spherical drop, it has the minimum energy. So if we want to break it into n number of smaller droplets, the surface energy will be increasing because the total surface area will be increasing. and that increase in surface energy is the work that the external agent has to supply. So that is the concept we'll use over here. Okay. So let's understand the application of that concept. So basically here what's happening is that when the spherical drop of radius equal to 8 millimeter is split into 8 identical smaller droplets, the total surface area of fluid will increase, which means that the surface energy
will increase.
will increase. And the work done by the external agent is equal to the increase in surface energy. So now we know the formula for surface energy above we've just seen. So we have to just use that concept. Okay. So first of all, 4 by 3 pi r cube, that is the volume of liquid initially, will be equal to 8 times 4 by 3 pi small r cube, where small r is the identical radius of the new droplets.
So smaller will be bigger divided by 2, no?
सर वो जब हम लोग डिस्ट्रीब्यूट करेंगे टोटल सरफेस एरिया डिक्रीज होगा.
Sorry, total surface area will be
डिक्रीजिंग नो.
no, it will be increasing. That is the whole point now. See, that's what we had learned last time, that any volume of liquid has minimum surface area when it is arranged into a single sphere. Okay, so when we are breaking it into smaller spheres, n number of smaller spheres, its surface area has to increase, and that's what we'll prove over here, how its total surface area increases.
Yes, sir.
So the total volume of liquid is remaining conserved. So the original volume of the single droplet on the left hand side is equal to the total volume of the 8 identical droplets of radius small r each on the right hand side. Okay. So from this you can automatically see that
Small r is equal to big r by divided by 2.
small r is equal to capital R divided by 8 to the power 1 by 3, so r by 2. So each one's radius has become halved, but total surface area, okay. So surface area initially S initially was equal to 4 pi r square. Now S finally has become 8 times 4 pi small r square. So you can see that it bars. It's increased by a factor of 100%. So the change in surface energy, the final surface energy minus the initial surface energy. So it is surface tension into final surface area minus surface tension into initial surface area. So this is our delta U, which is the work done by the experiment. So this will become 200 into 10 raised power minus 3, because it was in millinewtons. So now this is in Newton per meter. Okay. 4 into 3.14 into R was how much? It was 8 millimeters, right?
Yes.
So 8 into 10 raised power minus 3 square. This is the work done in joules. Minus 1 from here, minus 6 from here, minus 7. So anyhow, so this is a very typical type of question. So approximately something like 1.61 into 10 raised power minus 4. So that is why this is a process that you don't see happening naturally, that a droplet splits into smaller droplets. The reverse happens. If smaller droplets attack, they combine into one larger droplet because the potential energy reduces that way. But in order to break a single body of liquid into smaller droplets, work has to be done.
So can you please show the solution from the beginning?
Okay. Yeah, Rakshit, I will take you to the notes above also. let everyone finish with the solution of this first, then. Okay, so hope this is clear. So we'll come back to this. Let's just go over the notes before this ones. Okay, so let's move on. Okay, the next property of a liquid associated with surface tension we'll discuss is this concept of excess pressure inside a spherical surface, or on the concave side of a spherical surface. So we'll start by understanding the excess pressure inside a spherical drop. So if we just consider first a solid spherical drop of liquid of whatever radius r, and the surface tension surface is T, or of the liquid is T. So this is a solid spherical drop. Liquid which has surface tension equal to T and radius of the drop is equal to R. Okay. Now if you imagine that you have split the spherical surface into two equal halves, and you are kind of making a free body diagram of half the surface. So we are not making a diagram of half the sphere of liquid, but rather half of its surface. So considering this is half the surface. The given spherical drop. Now suppose the internal pressure that is P, and the external pressure is P naught. Okay, then this will experience force vectors like this due to external pressure. This is because of the external pressure. It will experience force vectors like this because of the internal pressure. And it will experience force vectors like this because this circle is in contact with the rest half of the spherical surface. Okay, so this force due to surface tension. So if you consider on this spherical or hemispherical surface now, there will be a net force in this direction due to surface tension. There will be a net force due to external pressure in this direction. And there will be a net force due to internal pressure in this sort of direction. So here, the net force due to surface tension on this half surface. Now this one we can easily understand. If on the hemispherical surface, this line of contact here, which is a circle, if we take a section of length dl, it experiences a force which is surface tension into dl. So this will just become surface tension into integration dl over the circumference.
Sir, in this case, we'll take surface integral.
No, it's not. See, surface tension acts per unit length. You understand? So this hemispherical shell, it's in contact with the left half hemispherical shell. So what is the line of contact? It's that circle.
Oh,
You understanding, no?
right.
For the pressure force, yes, we will have to take surface integration, but for the surface tensional force, it's a length integration. Got it, no?
Yes, sir.
So this one will become surface tension into 2 pi r. But yeah, the other two we will see will have to come from surface integrations, which we will do in a minute. Okay. So F naught is the net force due to external pressure. Now F naught will come out to be P naught into pi r square. This can be shown by surface integration, or it can also be shown on the other hand by just employing logic also. We'll see both the methods. Okay. And F is the net force due to internal pressure. So again, this F will come out to be P into pi r square. So now when we see the balance of forces, okay, so this equilibrium of the hemisphere or the hemispherical shells equilibrium could be established by the fact that F balances the force due to external pressure plus the surface tensional force. So this will give us the result that the excess pressure it's 2T by R.
Yes, sir.
So I will show you how come that force is P into pi r square or F naught is P naught into pi r square. That also we will see. But more important for us is this formula right now, that the excess pressure inside a spherical drop is given by this formula 2T by R, where T is the surface tension and R is the radius of the spherical drop. Okay. So I will just minimize this a little bit and you can go through this once. Then we will discuss about how to show that this force F and this force F naught are P into pi r square and P naught into pi r square respectively, even though the surface area of the hemisphere is actually 2 pi r square. Okay, but because there is component involved, at each point the force is acting in a radially inward direction towards the center, whereas the net force is along the axis. That is why it comes out to be this.
Yes, sir.
Okay, so next let's understand how we get these two forces because of the pressure, the external pressure and the internal pressure. So one way is to understand this logically, which is quite easy. So logically, if we take a different situation where we consider a solid hemisphere in an external pressure, uniform external pressure environment of pressure P naught. Okay, so now this is a different situation. We are considering arbitrarily that we have some kind of a solid hemisphere which is existing in a uniform pressure field where the external pressure is P naught. So this surface will experience force vectors like this, but also this surface will experience force vectors like this. So this side will experience a net force of, let's say, F1 like this, and the curved surface on this side will experience a net force of F2 like this, but F1 will be equal to F2 because the net force on a solid body in a uniform external pressure field must be zero. So now you can see that this force is P naught into pi r square, and this force was by surface integration on the hemispherical surface. So instead of doing that surface integration, we can just show by logic how it is equal to this quantity.
So F1 क्या है sir? वो नहीं समझ रहा.
Is the force on, now we are considering solid hemisphere, no? So on the
Okay. Sir.
left surface, no? So because we are considering a solid hemisphere, whereas F1 is the net force on the plane surface, like a disk, due to external pressure P naught. So F2 accordingly comes out to be P naught into pi r square. So that is the logic why in the previous one. So this is the logical method to understand this. Okay. On the other hand, we can also understand it by integration. So this is a good exercise in integration also. So we'll come back to this. Let's understand it by integration also first. So by integration, what we'll have to do is we'll have to divide that hemispherical surface into rings. And we have to consider the force due to pressure on any one ring first, and then integrate it like that. So if this is the center of curvature of that hemisphere, we will first have to consider
Two small rings of D.
we'll have to consider one thin ring
Yeah.
Like this. So this thin ring is, first of all, let's say, of thickness dl, which will become r d theta.
Yes.
So it's at an angular position theta. Its own radius is small r, let's say. So this thin ring, it has a radius small r, which is capital R sine theta, and a thickness dl, which is r d theta. So it has an area which is circumference into thickness. Like this, okay.
This is about
Now,
this is about thin ring, right?
yeah, this is the thin ring. Okay. Now we consider the force on the thin ring. So to understand that if you take within that thin ring, now if you take a small area, delta A over here, then that experiences a force, delta F, like this, which is pointing towards the center of P naught into delta S. Okay. But then on this side, there is another force of the same side. So what happens is, for these two forces, the sine
Cos
components
components.
cancel and the
Yes.
cos components add. Okay. So that is why on the whole ring, if we consider the force, it will be a force in this sort of direction. So dF is the net force on the thin ring due to external pressure. Right, let's write this like this. So you can see that over here, delta F cos theta is the adding component, and delta F sine theta is the cancelling component.
So this is the external pressure force, right?
Yeah, so this dF naught over here, this dF naught will be like that summation of delta F cos theta for the entire ring. So that will become P naught into area of the ring's cos component.
Yes, sir.
So this will become
So
P
what-
naught into
yes.
2 pi r square cos theta d theta, sorry, sin theta d theta for the area, but into another factor of cos theta.
Yes, sir.
So this becomes,
सर वो खाली pi r square नहीं होगा.
sorry,
Area will be equal to pi r square.
नहीं, एरिया पाई आर स्क्वायर क्यों होगा बेटा, थिन रिंग है ना, रिंग का एरिया क्या होता है, सर्कमफ्रेंस इनटू थिकनेस ना.
Okay, sir.
So this is the force that is acting on that thin ring alone. So now the net force that is acting because of external pressure on this entire hemisphere will come from integrating this for all the rings. On the hemispherical surface. So on the hemispherical surface, the rings are such that theta starts from 0 going up to theta equal to pi by 2.
So this is the surface integral, right?
This is a surface integration, yes.
डबल इंटीग्रल ना, मतलब डबल
नहीं
इंटीग्रल
बेटा, डबल इंटीग्रल क्यों करेंगे? डबल इंटीग्रल आपके सिलेबस में भी है क्या? What is the need of doing double integral? I've explained to you that on the single ring, you sliced it into rings. So on each ring, the component of force that is contributing towards the net force is the cos component. So it is pressure into area into cos theta. Now you have to integrate for all the rings.
Okay.
Okay, there's no need to unnecessarily complicate things. So now you have to just complete this integration with the limits, and that will show you why it is P naught into pi r square. So anyhow, we'll come back to this. You can start by this actually first. Okay.
So वो integration का value will become 1 ना, so that will become 2.
Yes. So you complete that integration, put the limits. You can show that it will show you the same thing that.
Yes.
Sir,
Yes.
sorry sir, I thought my connection problem.
Okay, so now complete this integration of sine to theta, put the limits, and you can show that it will come out to be the same. Okay, so so we get the same quantity that we got by the logical method also.
Yes, sir.
And the important thing now is that the pressure difference delta is equal to 2T by R.
So here this T is the surface tension, no?
Yes.
Yes.
Okay, now Let's first look at a couple of applications questions based on this. So in addition to this concept, one more thing we should understand, that if we are talking about a bubble instead of a solid droplet of solution, like a soap bubble, then the excess pressure inside will become double of this because it involves two surfaces. A bubble is basically a thin shell or like a thin film of liquid which is spherical in shape. So that film consists of two surfaces, an outer surface and an inner surface. So for a spherical bubble, basically a spherical film of liquid. For example, a soap bubble. So the situation there is that we are talking about this kind of situation. It's a thin shell of liquid. So there is air inside. There is a spherical thin shell or a film of liquid. So it has got two surfaces of liquid. Let's say the air inside is at pressure P. The air outside is at pressure P naught. This is the outer surface. This is the inner surface. So the pressure inside will be equal to the pressure outside plus 2T by R plus 2T by R. Because there are two surfaces whose radius is more or less capital R. So this is from the outer surface. It's from the inner surface. So the excess pressure inside becomes 4T by R in case of this kind of situation, a spherical bubble, which is basically like a thin spherical film of liquid or like a thin shell of fluid, as opposed to the excess pressure inside a solid spherical volume of liquid. Make sure you understand the difference between the two.
Sir,
Yes.
how will be the outer layer come in the after against the change in pressure? Yeah.
Any spherical surface is creating a change in pressure going from its convex side to its concave side of an increase of 2T by R.
Okay.
Okay, so here there are two surfaces back to back. So they are creating two pressure changes.
Okay.
So,
Hmm.
so the surface tension equations for specific cases, or how many we have them in the syllabus?
I have not counted. You can go through the chapter in any standard reference book and count the number of formulae we have. But it's a very easy chapter, and most of the questions are formula based. Okay. Okay, so now let's understand a question based on this.
So could you go up 1 second? Okay, sir.
Now, in our next example, we have this kind of a situation. Let's say we have two soap bubbles which are of different radii. This has a radius of 6 millimeters, and this has a radius of 4 millimeters. So two soap bubbles come in contact. So as they come in contact, situation becomes something like this. Now here there will be some kind of an interface between the two, which I'm not drawing. Okay. So assume their walls, the part in contact, do not break. They're just in contact. They just stick together. So find the radius of curvature the portion in contact, and also which side will the center of curvature be for this portion. Okay, so just try out this concept. We will discuss in a moment. Okay. So basically you can approach it like this, that if the external pressure is P0, then the pressure of air inside this bubble is P1, the pressure of the air inside this bubble is P2. So here that situation remains the same because this contact surface, it has not been breached. So the air on this side is still at its pressure P1, which is different from the air on this side. So that will cause a certain curvature for this part which is in contact. Okay. The common part of the shells which is in contact will exist at some kind of curvature. So now you can use the formula from above, and you can see that even though the value of surface tension is not given to us for the soap solution, independent of the value of surface tension, we can find the radius of curvature of the particle. Yes, Dhruv, that is correct. Very good. Okay, so what you can see here is that P1 is equal to P naught plus 2T by R1. And here P2 is equal to P naught plus 2T by R2. Okay. So you can see that P2 is greater than P1. So that same concept applies here. P2 is greater than P1. That means this surface will be something like this. Where they are in contact, this surface will be something like this. So the center of curvature will be somewhere on this side.
Sir, it should be 4T, no?
Yeah, correct. So it's a bubble. Very good. Okay. So now if this radius of curvature is R, now you can see that the pressure difference should be such that P2 minus P1 should be 4T by small r. Okay. And from here, from these equations, you can see the value of P2 minus P1. So if you substitute this information, you can understand this. Okay. So just complete this joining.
So sir, we have to just find in terms of R1 and R2.
Okay, so you'll get this formula here. And you can see the direction, the side on which the center of curvature is there.
They're on right side, no? With greater pressure.
Yes. Okay, so it will be concave towards the side which is having smaller radius of curvature. I mean, the smaller bubble will have the concavity. It will be convex on the side of the larger bubble.
Okay.
Okay, so now we come to the final aspect of this chapter, surface tension. The concept of contact angle, and related to that, capillary action or capillary rise of a liquid. So let's start with contact angle. We generally denote with the symbol theta c. So it's basically the angle between the liquid surface a solid surface that are in contact. So for example, if you consider a situation like this, that you have a glass container with water or any other solution or any other fluid inside it. So what we'll observe is that typically a fluid surface will be like a horizontal plane, okay? But exactly at the point of contact, there'll be a slight bending of it like this. The contact angle will not be 90 degrees. That bending happens because of the relationship between the adhesive forces between the glass surface and the liquid molecules. Suppose it has a surface tension of T. So when we visualize this part a bit, so we'll get a situation like this. The glass wall, the container. Now the fluid inside, at the point of contact, the surface is a bit bent like this. You have a kind of a curvature. So if we draw a tangent to the surface at the point of contact, that tangent is making some angle theta with the vertical or with the wall surface. So that angle theta is the contact angle. Angle of the tangent to the liquid surface at the point of contact. With respect to the vertical, which is basically the solid surface. Now this occurs. So typically for most liquid solid interfaces, like this, the contact angle will be less than 90 degrees. Okay, but there are exceptions. Example, mercury and glass. The contact angle is nearly 140 degrees for that. Okay. So if you look at a glass container with mercury inside it, then the surface of mercury is bent like this at the point of contact. It's bent like this. So tangent at the point of contact, that will be making an obtuse contact angle. Now this contact angle situation occurs in the first place because of cohesive and adhesive forces, the way they act. The liquid molecules at the surface near the point of contact, these molecules experience adhesive forces like this and cohesive forces like this. So adhesive forces are the attraction forces between solid and liquid molecules. And cohesive forces you know already. So most liquids have this situation because the adhesive forces dominate. But certain exceptional cases exist like this one, where basically what happens, cohesive forces dominate. So this is the phenomena of contact angle. Now the value of contact angle for a given liquid solid interface is a material property of that pair of materials. For example, water with glass has a contact angle of nearly 0 degrees, or very small contact angle. But water and some other surface like stone or wood or something will have a different contact angle. Similarly, glass and mercury has a different contact angle compared to glass and water. So it is this phenomena of contact angle also which creates the situation by which capillary reaction. Hence the two concepts are interrelated. Yes, sorry.
ग्लॉस की जगह कोई और मटेरियल होगा सॉलिड, एक डिफरेंस होगा क्या है?
Yes, I told you, no, it's a property of the pair of materials. Huh?
Sir,
Yes.
what have you written beside FA in the adhesive forces diagram to the left?
Yeah, adhesive forces, it's an attraction force between solid and liquid molecules.
No, sir, above the tangent, like there's an FA and then there's something like IA. What is that?
No, those are both adhesive forces. Okay. Adhesive forces act in the direction like liquid molecules which are there at the surface at the point of contact. They are experiencing forces towards the glass, sort of upwards. Okay. Whereas they are being pulled down by cohesive forces. So if the adhesive forces dominate over the cohesive forces, they both FA. Okay. Okay, now we'll see the next thing that because of this phenomena of contact angle only, if we put a thin open tube, okay, inside an open liquid surface, typically which is such that the contact angle is acute, then liquid rises in that. Okay. So a capillary is basically a thin cylindrical tube kind of thing. So for example, suppose so this is the open surface of, let's say, water or some liquid. And in this we insert a narrow glass capillary or even a plastic capillary, anything which is transparent so we are able to see. Observing is that the liquid will first of all have a, there will be a certain amount of rise of the liquid level inside the capillary. And secondly, as the liquid rises, the surface of liquid inside will be a curved sort of meniscus like this. It will be like a concave surface when viewed from above. And this angle, this will be the natural contact angle. So this H over here is called the the capillary rise. So as it turns out, if the radius of the capillary tube is capital R, the contact angle is this much, and the liquid has a surface tension equal to T, then the formula for the capillary rise is 2T cos theta, the contact angle, upon density into radius of the capillary into G. So there's a very easy way to prove this formula, and it's as a result of that pressure difference that is created across a concave surface of liquid or across a spherical surface of liquid. But more important than the derivation is the formula itself for us. Okay, so basically, to answer your question, Shikhar, why it curves like this is the natural behavior of that liquid and solid interface, that because of the cohesive forces that, let's say, the glass capillary is applying on whatever liquid there is here, like water. So the surface has to bend like this, because whenever there's an interface, this is how the liquid naturally bends. Now, the moment the liquid bends, it creates a pressure difference, and that causes it to rise. So let's understand the mechanism of that pressure difference. So now, making a more magnified diagram of it. So what's happening inside the capillary is that the liquid interface is like this. because of the natural tendency of the liquid to bend like this. Okay, so this is called the meniscus of the liquid. Basically a concave surface of the liquid. Okay, so this happens because of the behavior of the liquid in terms of contact angle. So if we draw tangent to the surface here, draw tangent to the surface here, symmetrical. These both will be at the same contact angle. So that also shows you that the liquid surface, the normal to the surface is this, perpendicular to the tangent. The normal to the surface here is this, perpendicular to the tangent. So this here is the center of curvature of the liquid meniscus. C is the center of curvature of liquid meniscus. Okay. And R is its radius of curvature. Again of the liquid meniscus. Okay. Whereas if we drop this perpendicular here, this is capital R. This is the radius of the capillary. So now you can see in this angle will be the contact angle, okay, because this angle has to be 90. So we have the relation that capital R by small r is so this is the first important thing. Okay. Now related to this is so if liquid has risen to a height h, if you consider a point like this over here and a point just outside over here, another point C over here, another point D over here. Now you can see that pressure at B will be equal to pressure at A plus 2T by R, because B is on the concave side of a spherical surface. But pressure at B is also equal to atmospheric pressure. So pressure at A is equal to
T naught minus.
now pressure at C is equal to pressure at A plus rho GH, and that is also equal to pressure at D, and pressure at D is equal to atmospheric pressure. This is at an open surface. So combining these equations, now we get now taking the value of small r from equation 1 above. So this is how we prove, or more than prove, actually we understand the mechanism of capillary rise. So as the liquid comes into the tube, the surface of liquid inside the capillary is not a flat surface, it's a curved surface. So that is creating this pressure difference across these 2 points A and B. And that pressure difference is what causes the liquid to rise to compensate for that pressure difference created. So with this, we complete the chapter of surface tension. It's actually like a sub-chapter. It's like a small part of properties of matter, you can say. Okay. So that's where we'll conclude today. And next time we will pick up viscosity, which is the last part of this section, properties of matter.
Sir,
Yes.
is h the distance till the lower part of the meniscus or the upper part?
There's not that much difference because the radius of the curvature of the capillary is small. No?
Okay.
Understand? No? So compared to H, that difference in the height right at the wall versus at the depression point of the meniscus is not so significant.
So what do we take?
It's the point A, na, you can see. In the diagram, H is the height between the point A and the point C. Na? The point A is just below the meniscus.
Okay.
Okay, people, so hope this concept is clear of capillary rise and the derivation of the formula. Okay. So with that, we conclude today's session. Thanks for attending. Wish you all the best.
Thank you, sir. Bye, sir.